In this typical initial rate analysis problem, we're trying to determine the rate law for this reaction, which includes two different reactants, this cobalt amine complex and OH minus. And we have a table that includes data from measuring initial rates of reaction, so R naught, initial rates of reaction. And remember that these are measured by getting the slope of the concentration versus time curves at 0 time. Then we have in the other two columns the concentration of cobalt amine that we started with. So the sub-zero there means the initial concentration of cobalt amine, and the initial concentration of the OH minus that we started with for 3 different trials. And what we want to know is what the rate law, so in other words, what is the order of reaction for both of the reactants, and the rate constant, that is the proportionality constant between rate and the rate law. So we start by remembering that in general, the rate law can be written as the rate equals some rate constant times the concentration. I'm going to abbreviate this cobalt concentration as just CO, time raised to some power, that's the order with respect to the cobalt complex, times the concentration of the OH minus, raised to a different power, that's the order with respect to the OH minus. So if we have 2 experiments where we've kept the OH minus concentration the same, so these trial 1 and trial 2, we have the OH minus concentration has stayed the same, but we've varied the cobalt amine complex concentration. And we can see that the rate has changed. The trick here is that if we take the ratio between rate 1 and rate 2, this will have to be equal to the rate constant times the concentration of cobalt raised to the nth used in experiment 1 in trial 1 times the concentration of OH minus raised to the m used in experiment 1 divided by the same thing for experiment 2. And since the hydroxide, the OH minus concentration, is kept the same between the 2 experiments, and because the rate constant does not depend on the concentrations, it will be the same between the 2 different experiments. When we take this ratio, we can see that the rate constants factor out and the OH minus concentrations factor out, because for trials 1 and 2, the OH minus concentration is the same. That means that the ratio in the rates is equal to the ratio in the cobalt amine concentrations raised to the nth power. And I know the rates. Rate 1 is 0.01 molar per second, and rate 2 is 0.02 molar per second. And that has to equal the ratio in the concentrations. So for trial 1, I have 0.005 molar, and for trial 2, I have 0.01 molar of the cobalt amine raised to the nth. So if I just calculate this out, this is 1/2, and it's equal to 1/2 raised to the nth. And so I can see right away that n has to equal 1, because 1/2 is only equal to 1/2 raised to the nth if I raise it to the first power, if I don't change the value of 1/2. So that tells me that the order with respect to the cobalt complex is equal to 1. So now I can do the whole thing again, but use trials 1 and 3, because in 1 and 3 the cobalt amine complex concentration stays the same, but the OH minus concentration changes. And so I can think about doing the ratio between the rate for trial 1 and the rate for trial 3, which will be equal to the rate constant times the cobalt amine concentration used for trial 1 times the OH minus concentration used for trial 1 divided by the rate constant, which doesn't change, times the cobalt concentration used for trial 3 times the OH minus concentration raised to the nth for trial 3. And in this case, the rate constants, again, will factor out because they have to be the same. But for trials 1 and trials 3, the cobalt amine concentration stays the same. And so I can factor out the cobalt amine concentration, and I can see that the ratio between the rate for trial 1 and the rate for trial 3 is equal to the concentration for the OH minus for trial 1 divided by the concentration for the OH minus for trial 3 raised to the mth power. And since I have a table of data, the rate for trial 1 is 0.01 molar per second. The rate for trial 3 is 0.1 molar per second. And the concentration of OH minus in trial 1 is 10 to the minus 11th molar. And the concentration of OH minus for trial 3 is 10 to the minus 12th molar. And that has to be raised to the nth power. So I can see that 1 over 10 is equal to 1 over 10 raised to the nth power. And so again, I can see that m is equal to 1 because the only way to make this statement true is for m to equal 1. So now I know that the rate law is equal to some rate constant times the cobalt amine concentration raised to the first power times the OH minus concentration also raised to the first power. So if I want to know what the value of the rate constant is, I just need to take the data from one trial, doesn't matter which one, and plug it into this equation and solve for K. So let's just take trial 1. We know that 0.01 molar per second is equal to whatever K is equal to times 0.005 molar times 10 to the minus 11 molar. And so we can see that 0.01 molar per second is equal to 5 times 10 to the minus 14 molar. If I divide by that, that will equal K, because I just need to solve this equation for K. So I divide by 0.005 times 10 to the minus 11, which is the same as 5 times 10 to the minus 14. And so when I do that, I get K is equal to 2 times 10 to the 11th per second. So the units of K in this case are per second.